Welcome back to my favorite universe. Today I want to talk about, of course, one of my favorite subjects, and that is rarefied phenomena, rarefied objects in the cosmos. Of course, there's a lot out there that's dense, but there's so much more that's rarefied that it's certainly deserving of its own presentation. And let's begin on Earth. Let's begin with what's most familiar. We've all been to a magic show and seen a magician with a top hat and pull a rabbit out of a hat. Well, that's usually described as pulling a rabbit out of thin air. Thin air. Air is something we think of as very low density, very rarefied. In fact, if someone didn't tell you there was air between us, you might not think there was anything there. You know there's air because wind blows trees and you see storm systems and you see all this, but if you just plopped here on Earth, there's no obvious measure that there's air there, but that there's anything there at all. Nothing blocking your view. But let's ask ourselves, what is this air made of? Well, we know it's got nitrogen and oxygen, sure. How dense is it? Well, let's look at how many nitrogen and oxygen molecules of our atmosphere at sea level air pressure would fit into a thimble, a cubic centimeter of volume. Well, that has about the same number of molecules as the number of grains of sand on an average beach. About a quintillion. One with 18 zeros. So there's nothing thin about air at all if you're counting molecules. But we still like thinking of air as nothing. In fact, that concept goes very far back. With something close to nothing. Look at the famous Aristotelian elements, earth, air, fire, and water. It's one of the base elements from ancient thinking. But in fact, there was a fifth element that was lighter than all four of those. A fifth element, a quintessence it was called, and that was the substance of the cosmos, space. And that rose above the earth and above the air because, in fact, it was even lighter than air. So it was not where earth is, it was in the heavens, filling the cosmos. Let's think a little more about this, the quintillion particles per cubic centimeter. There's a certain weight that has. We call it sea level air pressure, but pressure is a force per unit area. And so let's think of it as the force, as a weight. Let's take a square inch. Sea level air pressure is about 15 pounds per square inch. Now, what does that mean? It's something simple. It means something simple. Put a square inch on the ground and cut through the atmosphere a column of air, 1 square inch in cross-section, and start from the surface of the earth and go all the way out to the farthest reaches of the atmosphere. That is a column of air. It goes up hundreds of miles, even thousands of miles. Take that, put it on a scale, and weigh it. It's 15 pounds. That's what air pressure means. It is the weight of the column of air above. Well, what happens when you have a suction cup? You have a suction cup and you press it down onto the ground. You're removing the air that used to be inside that pressure cup, balancing the air all around it. Once you take out the air, the full weight of the 15 pounds per square inch is resting on the outside of that rubber. And you try to pick up the suction cup and you say, oh, it's sucking me down. No, the atmosphere is pressing down on the surface of that suction cup, preventing you from pulling it up. How much force do you need to lift it? Well, with the surface area of the suction cup. If it's 10 square inches, you need 10 times 15 pounds per square. You need 150 pounds to pull. And if you could put 150 pounds in it, you pop the thing right off the ground. That's how suction cups work. And the moment you lift it up, air swiftly swoops in to fill the vacuum that had been left there by pressing the air out in the first place. And so there's this old adage, nature abhors a vacuum. Wherever there's a vacuum, nature collapses down on it to get rid of the vacuum. And so we have this idea that somehow a vacuum is rare or uncommon or something that nature does not like. Well, I'm an astrophysicist, and my concept of nature is not just what happens on Earth's surface, it's what happens in the cosmos. And in the cosmos, in fact, nature loves a vacuum. And we'll see more about that in just a few moments. But let's keep playing with this notion of atmospheric pressure. If you go to a mountaintop, let's go to one of the highest mountaintops where there are large telescopes, Mauna Kea, Hawaii. In Hawaii, that is at 14,000 feet. It's not 15 pounds per square inch anymore. You're higher up. The column of air above you is shorter. There's less air, there's less pressure. In fact, it's about 10 pounds per square inch. There's less air. That also means, of course, there's less oxygen to breathe. So at the console for all of the telescopes, is an oxygen tank, and things orbiting relatively low compared with that, and we say that they're out in space. But in fact, the boundary of Earth's atmosphere can be defined by where the density of air is no longer distinguished from the density of space between the planets. At that point, you say, okay, Earth's air is here, and the rest of the solar system is there. But that being said, we know most of that air is compressed down at the lowest levels. In fact, 99% of all the air molecules on Earth is found below a height, below an altitude of 50 miles. There's still a little bit of molecules up above that, not many. In fact, conditions are wholly unlike what you find in the laboratory. It's very low density compared with sea level, compared with Mauna Kea, very low density. At those altitudes, 50 to 100 miles up, molecules collide less frequently. So the whole dynamic among the molecules has changed. Here's an interesting fact. There's a stream of particles coming from the sun. We call it the solar wind. Stream of charged particles. This is well known ever since we've been studying the sun. These charged particles travel through interplanetary space and they come near Earth. Since they have charge, they respond to the magnetic field of Earth. Positive charges go to one pole, negative go to the other, and they spiral down in towards Earth's magnetic poles. But it's not a free trip. There's atmosphere there. So they start colliding into atmospheric molecules. You know that begins to happen? Between 50 and 100 miles up. They never make it low down. As low density as that is, between 50 and 100 miles up, is high enough density for these things to hit. And when they hit, they excite the molecules. Molecules love getting excited because you excite a molecule, and when it, upon being excited, it says, okay, how will I de-excite myself? And one of the ways is it releases light, photons of energy, green light, yellow light, blue light. And as it releases this energy, it creates a display of lights in the sky, better known as the aurora. One of my favorite images of the aurora is not one taken from Alaska, although some of the best images, terrestrial images, come from there. My favorite is taken from the space shuttle. And we take a look at an image now. We see the tail end of the space shuttle. Space shuttle orbits a couple hundred miles above Earth's surface. You notice in this image that, of course, the aurora is lower in altitude than the space shuttle. And just look at the light emitted. That is the emitted light from molecules of Earth's atmosphere, having been excited by particles streaming from the sun. This only happens in very low density environments, such as what happens in the upper atmosphere. You get this in the northern hemisphere as well as in the southern hemisphere, and you might be more familiar with them as the aurora borealis and the aurora australis. Another place where material is thin is the sun, the solar corona. You hardly ever get to see the corona unless you're eyewitness to a total solar eclipse. I've seen one in my life, unforgettable. I was off the coast of Northwest Africa some years ago. And what happens is, of course, in a solar eclipse, the sun moves, the moon moves in front of the sun, eclipsing the sun, occulting the disk of the sun. And when that happens, when the light of the sun is removed, you see the glowing outer atmosphere of the sun, which is not bright enough to reveal itself when the sun is visible. When the disk of the sun is, you have to blot out the disk of the sun. Then you see the solar corona, the crown of the sun. The solar corona, we didn't know much about it for a long time. Like, what is it? It's just some glowing gas. What is it? That's what we assumed, but we didn't know much about it. Then we study the light. Take the light, pass it through a prism, and study the features of the light, the component colors. You pass light through a prism, it breaks up that light into its component color. Just the way sunlight moves through raindrops and makes a rainbow. Red, orange, yellow, green, blue, violet. Sunlight's composed of those colors. Do the same thing for the solar corona. And you can study what kinds of elements are present in that corona. And we found a signature of an element nobody had ever seen before. In fact, we invented a name for it, called it coronium, because we didn't know what it was. There was no laboratory counterpart for it. We didn't know where it might fit in the periodic table of elements. We didn't know anything. So we had this placeholder name for it. Turned out, under the low density conditions in the outer atmosphere of the sun, under very high temperatures, millions of degrees, iron emits a signature of light. Highly ionized iron. We're talking about iron that has lost most of its electrons. Ionized, heavily ionized. It has a spectral signature, unmistakable. But we had never ionized iron that much before. We had never subjected it to low-density environments such as the corona before. We had no way to understand it until we figured out that it was under very low density and very high temperature. And so the solar corona is an example of something that's quite visible and quite beautiful, but is also very, very low density in the cosmos. By the way, if it were much higher density, it might be more visible even with the sun in the picture. You really have to blot out the sun in order to see the corona. Temperature of the corona, millions of degrees. Millions. That's how hot you had to be to ionize iron as much as it got ionized. And the surface of the sun is a mere 6,000 degrees. And it remains a mystery how you can get something that hot sitting above something that cold. Major frontier of solar physics. We have ideas, but no true consensus just yet. Let's keep rising up. How about the asteroid belt? We all have a favorite vision of the asteroid belt as this shooting gallery. All right? Don't dare take your spaceship through the asteroid belt. They'll come and knock out your antenna. It'll be really dangerous. Now, wait a minute. Let's look at the facts. Take all the mass of the asteroid belt and combine it together and weigh it. How much is it? What do you get? You get about 2 or 3% of the mass of the moon. Of our moon. No, it's not some jumbo planet and all its that got shattered and all its debris is still there. It's like 2.5% of the moon. Now, of all that mass, put 75% of it in only 4 asteroids. And take the rest and scatter it for 100 million miles wide in an orbit around the sun, 1.5 billion miles around. That's the asteroid belt. Now, it's still more dangerous to go through the asteroid belt than to not go through the asteroid belt. But it is much less dangerous than most people ever think of it to be. Much lower density of material than we ever credit it for having. And of course, our 4 spacecraft that have gone to the outer solar system and have left, they're beyond the orbit of Pluto, that's Pioneer 10 and 11 and Voyager 1 and 2. Those 4 spacecraft travel through the asteroid belt without incident, just as we suspected. Let's keep going out into space. By the way, the density of matter in interplanetary space, we learned what it was on Earth. Sea level, what was it, a quintillion molecules per cubic centimeter. Out in interplanetary space, we're down to 10. 10 per cubic centimeter. Now, there's a vacuum for you. There's a vacuum. And that's about the best laboratory vacuums, but are also quite thin. Comet tails. Comet tails. Comet tails are long. Big comet tail. Good, like Comet Halley, 100 million mile long tail. Recently, Comet Hale-Bopp and Comet Hyakutake in the last several years, those comets were great comets. Great in the classical sense of the word great. You get a few of those in a lifetime, so make sure you put in your schedule to go see them, as many of us did. But what of a comet tail? As visible as they are, what are they made of? They're still thin. They're still thin. But they're remarkably visible for their thinness. They reflect sunlight and they emit light of their own for having been excited by the high-energy photons from the sun. So, yes, it's a visible stream. Not very high density. Yes, it's more dense than interplanetary space, but not by much. In fact, the comet pioneer, Fred Whipple, once described comet tails as the most ever made of the least. It's 1,000 times the density of interplanetary space, which is still small compared with ordinary Earth air. Now, let's quantify how thin the comet tail is, even though it's even though its density is high compared with interplanetary space. Let's take the whole tail, collapse it to atmospheric density, and ask how much do you have? That's a good way to compare. Take the 100 million mile long tail, say, let's make atmospheric pressure out of that. You could fill a cube maybe a half a mile on the side. That's all it is. Fred Whipple was right. It's the most ever made with the least. Now, when people first invented tools of spectroscopy, studying the light from objects and looking at what material was in them, what spectral signatures permeated the analyzed light, they found the comet tails had cyanogen in it, CN, a deadly poison. It would kill you post-haste. But when Comet Halley came around in 1910, people didn't know, the public didn't know about how low the density of the comet tail was, and how it was barely any. No matter what you found, it's not enough to do anything to anybody. What scared people is that we knew that Earth was passing through the tail of Halley's comet. It passed through the tail. It actually did, intersecting some of that gas. People got all worried. Charlatans were selling anti-comet pills, making a lot of money on people's fear. But if you knew a little bit about how thin it was, you would have saved your money. So knowing about the rarefied phenomena in the cosmos can be good for your pocketbook on occasion. That takes us to something not widely appreciated. Let's look at the density of the sun. It's gaseous, but you might think it's like really dense. It is very dense in the core, less dense on the surface. But if you averaged it, it's about the density of water. So too are human beings. That's kind of interesting. Water has a density of 1 gram per cubic centimeter. Human beings, we basically float or sink or somewhere in between. So that puts us at about 1 gram per cubic centimeter. The sun is actually a little heavier. The sun is just a little heavier. 1.4 grams per cubic centimeter. So if you took a scoop of the average material of the sun, it would sink in your bathtub, but it would not sink that fast. What happens in 5 billion years? The sun is about to die in 5 billion years. It swells up, becomes a red giant. It becomes 100 times bigger in diameter than it is now. Of course, it didn't add, there's no mass that got added to it, so the average density drops. It drops to 1/millionth its current density. By then, the surface of the sun is very close to Earth. That's bad. Bad day on Earth. The atmosphere would evaporate. The oceans would come to rolling boil. They too would evaporate. Life would vaporize. Ignoring those complications, what we find is that the material of the sun, as rarefied as it is, Earth is trying to orbit the sun, plowing through some of that material. And that resists the motion of Earth, and Earth ends up losing its orbital energy and spiraling into oblivion, down into the center of the sun. That's going to happen in 5 billion years. So as rarefied as the sun becomes as a red giant, it will still impede the motion of the Earth. Let's go to interstellar space. We go beyond the planets, beyond the Oort cloud of comets that surround the solar system. Interplanetary space is even less dense there. By the way, the nearest stars are far. Our space probes, Pioneer 10 and 11 and Voyager 1 and 2, at those speeds, it'll take 25,000 years to get to the nearest star. It is far. It is far. It is big. It is empty. There, you'd be hard-pressed to find a couple of atoms for every few cubic centimeters. Just 1/10 what it is between the planets. Much better than most vacuums ever created on Earth. Gas clouds that live between the stars, they are rendered visible. Much like comets that come near the sun, gas clouds in the galaxy are rendered visible if they're near a star. The star reflects light off of them, and they get excited and release light from their own atoms and molecules. And we use special telescopes to detect this. In these gas clouds, there was another spectral feature that no one knew about, and no one had ever seen before. In the nebulae of space, we found an element. We didn't know what to, we call it nebulium. You ever hear that? Nebulium. What did nebulium turn out to be? It turned out to be oxygen in a peculiar state of temperature and density. What kind of density? Very low density. The kind of densities that were very uncommon on Earth and very hard to create in the laboratory. Although now we can do it routinely. Interstellar space, it's got stars, it's got gas clouds, it's pretty empty between those places. However empty that is, it's emptier between the galaxies. Between the galaxies, that's empty. That's empty. There's no dust, there's no stars, there's no planets, there's no moons, there's no comets, there's no comet tail. It's empty. It's as empty as you could possibly find. And then you get one atom in a cubic meter. A cubic meter. Another way to think of it is, take a 200,000 kilometer cube. How many atoms are in that 200,000 kilometer cube? About the number of atoms in the air in your refrigerator. That's empty. That means most of the entire universe is a vacuum. As I said earlier, the cosmos loves a vacuum. Now, you might have heard that the universe is expanding. There's not enough mass in the universe to exhibit enough gravity to halt that expansion and bring it back. But we can ask the academic question, how much mass would it take to balance the expansion? The whole universe had 10 particles per cubic meter. That would be enough to halt the expansion and send us right back from whence we came. That doesn't sound like much. It's not that much. Just more than what it is now. But what again of this notion of perfect vacuum? Suppose there were no particles. Does that even have any meaning? How do you do that? Does such a place exist? Well, We see from our favorite vacuum pump, once again, that we're making great strides to try to create the vacuum of interstellar space, intergalactic space. It may be impossible, but let's imagine the day comes where we can create the perfect vacuum, like the perfect storm, the perfect vacuum inside of this cavity. What would we measure? Turns out, the field of quantum mechanics, a very successful branch of physics, discovered in the 1920s, added to in the decades that followed. That's a description of nature on its smallest scales. It tells us what atoms and molecules are doing, which is wholly unfamiliar to the kinds of things we see happen in everyday life. All kinds of new forces take effect. Forces of quantum mechanics, new forces of physics, new behavior of material. Turns out, quantum mechanics predicts that in the vacuum can't really be a vacuum. That it's seething with these things called virtual particles, which are particle pairs, matter and antimatter pairs that pop into existence, annihilate, and then go out of existence again. And they live too short a period of time to measure their existence. Now, this just sounds like a cartoon. It sounds like science fiction. It sounds like just, not science fiction, it sounds like fiction. But so much else that quantum mechanics has predicted has come true. That no one has the audacity to assume that this prediction is somehow going to be false when everyone else turned out to be correct. So, what does that mean if particles are popping in and out of existence in the vacuum? You can measure what effect this has on the environment, and it creates a pressure. A pressure. A density of energy that has an opposite effect of gravity. Instead of bringing things together, it pushes things apart. We call this the vacuum energy. And you know something? If you calculate how much vacuum energy is in the entire cosmos, you get a number that's kind of insane. Something's wrong with our calculation. But we do calculate that, in fact, there's a pressure on the cosmos that will never let us recollapse, no matter how much matter we would ever find. Recently, we discovered that, in fact, the universe has a kind of an anti-gravity pressure operating on it. It's a recent discovery, a few years ago. This is this famous dark energy. Nobody knows where it came from. Nobody knows what it's made of, but we know it's there. This vacuum energy from these seething virtual particles predicted by quantum mechanics could explain that. Except that when you calculate it, the numbers are wildly different from each other. So we don't know what the problem is. It remains a frontier of our understanding of the cosmos. But we feel a little better that there is something that we know about that can create this negative pressure on the universe, forcing it to expand exponentially into the future. Even though the calculation doesn't work out, it's far too much compared with what we see. But it's encouraging because before we had these ideas, there was nothing we could conceive of that could resist the titanic forces of gravity on a cosmic scale. Well, is there some limit to this nothingness? I talk about empty space, but I still use the word space. I'm still saying there's a thing called space. Suppose there was a place where there wasn't even space. What is that? Maybe that's outside of our universe, if there is such a concept. Because if space there is nothing, then perhaps outside of our universe, where there is no space, there's not even nothing. What shall we call that? We would call it nothing.